Hello, and welcome to Sleep Archive. Imagine a place where the rules of the universe break, a place where matter is crushed into nothingness, where time stands still, and where light itself cannot escape. It is not science fiction, it is the inevitable endpoint of gravity's victory. We call them black holes. For decades, they were just mathematical ghosts, errors in Einstein's equations that physicists tried to ignore. They seemed too absurd to be real. How could a star collapse until it vanished from the visible universe? How could a hole exist in the fabric of reality? But today, we know they are not only real, they are everywhere. They anchor the centers of galaxies. They wander the dark spaces between stars, and they power the brightest beacons in the cosmos. They are the sculptors of the universe, consuming matter and spitting out energy that shapes the birth of new stars. In this journey, we will walk the edge of the abyss. We will see how a dying sun can tear a hole in space-time. We will discover why falling into a black hole might look like freezing forever to your friends, while you plunge toward a destiny of infinite density. We will explore the paradox that threatens the foundation of quantum physics and the possibility that our entire universe might just be a hologram on the surface of a giant black hole. Prepare to leave logic behind. This is the science of the singularity. To understand a black hole, you must first understand a star. A star is not a solid object like a planet. It is a ball of gas, mostly hydrogen and helium, held together by its own immense gravity. It is constantly trying to collapse, to crush itself into a single point under its own weight. So why doesn't it? Because a star is also a nuclear bomb. Deep in its core, under incredible pressure and temperature, millions of degrees, hydrogen atoms are smashed together to form helium. This is nuclear fusion. This reaction releases a tremendous amount of energy. That energy pushes outward. A star is a balance between two titanic forces, gravity pulling in and fusion pushing out. This state is called hydrostatic equilibrium. For billions of years, the star is stable. Gravity tries to crush it. Fusion pushes back. It is a stalemate, but eventually, the fuel runs out. When a massive star, at least 10 to 20 times the mass of our sun, burns through its hydrogen, it starts fusing helium, then carbon, then neon, then oxygen, then silicon. Each stage happens faster than the last, desperate to generate enough outward pressure to hold back the crushing weight of gravity. Finally, the star tries to fuse iron. Iron is the cosmic killer. Fusing iron does not release energy, it consumes energy. The moment iron is created in the core, the outward pressure stops. The stalemate is broken. Gravity wins instantly. In a fraction of a second, an iron core the size of Earth collapses to the size of a city. The outer layers of the star rush inward at 25% the speed of light. They slam into the hyper-dense core and bounce off in a shockwave of unimaginable power. This is a supernova. The star explodes with the brightness of an entire galaxy. What is left behind depends on how much mass remains in the core. If the core is between 1.4 and 3 times the mass of the Sun, the collapse stops. The protons and electrons are crushed together to form neutrons. The core becomes a neutron star, a ball of city-sized nuclear matter so dense that a teaspoon of it would weigh 1 billion tons. But if the core is more than 3 times the mass of the Sun, even neutrons cannot stop the collapse. The strong nuclear force, the force that holds atoms together, is overwhelmed. There is no force in the known universe strong enough to halt the crush. The core collapses past the size of a city, past the size of a pinhead, past the size of an atom. It keeps shrinking until it has zero volume but infinite density. It has punched a hole in the fabric of space-time. A black hole is born. To understand why a black hole is black, we have to talk about speed, specifically escape velocity. Imagine you are standing on a baseball field. If you throw a ball straight up, gravity slows it down until it stops and falls back to your glove. If you had a cannon and fired the ball faster, it would go higher before falling back. But if you could fire the ball at a specific speed, about 25,000 miles per hour, it would never come back. It would break free of Earth's gravity and drift into space forever. This specific speed is the escape velocity. Escape velocity depends on two things: how much mass the planet has and how close you are to its center. If you add more mass, like making Earth as heavy as Jupiter, the gravity gets stronger. The escape velocity jumps to 135,000 miles per hour. But here is the trick. You don't have to add mass to increase gravity. You can just make the object smaller. If you could crush the Earth down to the size of a peanut, keeping all its mass, the gravity on the surface of that peanut would be insane. You would be standing just millimeters away from the entire mass of the planet. The escape velocity would skyrocket. Now we hit a wall. A universal wall. In our universe, there is a speed limit. Nothing, absolutely nothing, can travel faster than the speed of light in a vacuum. This is c. It is roughly 186,000 miles per second. It is the speed of causality itself. In the late 1700s, a geologist named John Michel asked a simple question. What if a star was so massive or so small that its escape velocity was greater than the speed of light? He called them dark stars. If the escape velocity is faster than light, then light itself cannot leave. If you shined a flashlight up from the surface, the beam would rise, slow down, stop, and fall back down like the baseball. Since our eyes only see light, an object that traps light becomes invisible. It becomes a silhouette against the universe. It becomes a black hole. So, a black hole is not necessarily a hole in the ground sense. It is an object where gravity has become so intense that the exit speed exceeds the speed limit of the universe. Because nothing can go faster than light, nothing can ever leave. The scariest thing about a black hole is that it is silent. It has a boundary, but it is not a physical wall you can touch. It is a mathematical line in the sand. We call this boundary the event horizon. It is the point of no return. Imagine a river flowing toward a waterfall. As you get closer to the edge, the current gets faster. If you are in a boat with a motor that can go 10 miles per hour and the current is only 5 miles per hour, you can turn around and drive upstream to safety. But at the edge of the waterfall, the water is falling at 20 miles per hour. Even if you turn your boat around and floor the engine, you are moving backward. You are fighting a current that is faster than your top speed. You are going over. In a black hole, space itself is the water, gravity is the current, and the speed of light, c, is the boat's top speed. At the event horizon, space is falling into the hole at the speed of light. Because nothing can travel faster than light, nothing can swim upstream. Even a photon of light trying to fly straight out is dragged backward into the darkness. This boundary is defined by the Schwarzschild radius. Every object in the universe has a Schwarzschild radius. It is the size you would have to crush that object down to in order to turn it into a black hole. For the Earth, that radius is about the size of a marble, 9 millimeters. For the Sun, it is about 2 miles. For you, it is billions of times smaller than a proton. If you were to float toward a black hole, you wouldn't feel anything when you cross the horizon. There is no sign, no barrier, no bump. It is just empty space. You would simply drift across a line where escape becomes impossible. Once you are inside, the geometry of the universe changes. Outside the hole, you can move in any direction, up, down, left, right. You can choose to go back the way you came. Inside the hole, space is so twisted that toward the center becomes the only direction. In fact, the center is no longer a place in space. It becomes a moment in time. Just as you cannot stop tomorrow from happening, you cannot stop yourself from hitting the singularity. Moving forward in time means moving inward in space. All paths lead down. At the exact center of a black hole lies a concept that gives physicists nightmares. It is the final destination of everything that crosses the event horizon. We call it the singularity. If the event horizon is the point of no return, the singularity is the end of the line. But what exactly is it? To understand it, we have to look at how Albert Einstein described gravity. He did not see it as a magical pulling force. He saw it as a physical curve in the fabric of space and time, general relativity. Imagine space as a large flat trampoline. If you roll a marble across it, the marble travels in a perfectly straight line. Now, place a heavy bowling ball in the middle. The trampoline sags. If you roll the marble now, its path bends toward the bowling ball. The marble isn't being pulled by a mysterious magnet. It is simply following the curved shape of the trampoline. The heavier the object, the deeper the curve. The Earth makes a small dimple, the Sun makes a deep bowl. But a black hole takes all the mass of a dead star and crushes it down endlessly. Imagine taking that bowling ball and compressing all of its weight into the microscopic tip of a single needle. If you press that infinitely heavy needle into the trampoline, it does not just make a deep bowl, it punctures the fabric. It creates a sinkhole that drops down forever. This is what we call infinite curvature. The math of general relativity breaks down completely at this point. If you plug the conditions of a black hole into Einstein's equations, the result you get is infinity. And in physics, getting infinity as an answer is usually nature's way of telling you that your theory is broken or incomplete. At the singularity, all the matter that ever fell into the black hole, shredded stars, swallowed planets, trapped light, and cosmic dust, is crushed into a space smaller than a single atom, smaller than an electron. It is compressed into a literal mathematical point of 0 dimensions. Since density is defined as mass divided by volume, and the volume of this point is 0, the density becomes infinite. But here is where the universe throws a wrench into the gears. We have another set of rules called quantum mechanics, the physics of the extremely small. Quantum mechanics tells us that you cannot compress things infinitely. Particles are fuzzy. They vibrate and require a minimum amount of physical space to exist, the Pauli exclusion principle. So, we have a profound contradiction. General relativity demands that the singularity must be infinitely small. Quantum mechanics demands that it cannot be infinitely small. They absolutely cannot both be right. The center of a black hole is the only place in the universe where our two most successful fundamental theories of reality clash so violently. Until physicists discover a working theory of quantum gravity, a new set of rules that marries the physics of the heavy with the physics of the small, the true nature of the singularity will remain a total mystery. It is a locked door at the very bottom of the universe, and we simply do not have the key. If you were to jump feet first into a black hole, you might expect to simply fall in the dark until you hit the center. But gravity is not uniform. It is a gradient. It gets stronger the closer you get to the source. On Earth, this difference is so tiny we cannot feel it. The gravity pulling on your feet is technically slightly stronger than the gravity pulling on your head, because your feet are closer to the center of the planet. But the difference is mere fractions of a percent. Our bodies easily hold themselves together. Near a black hole, this difference becomes monstrous. We call this a tidal force. It is the exact same physics that causes the moon to pull on the Earth's oceans and create the tides. The water on Earth facing the moon is pulled harder than the water on the opposite side of the planet. Imagine floating a few hundred miles above a black hole. The gravity pulling on your toes is suddenly millions of times stronger than the gravity pulling on your head. Your feet are accelerating downward vastly faster than the rest of your body. You are being stretched. At the same time, because all paths lead directly to an infinitely small point at the center, the left side of your body is being pulled slightly to the right, and the right side is being pulled slightly to the left. You are being compressed inward. You are stretched vertically and crushed horizontally. The late physicist Stephen Hawking coined the perfect, albeit slightly gruesome, term for this exact process: spaghettification. Long before you ever reach the singularity, the chemical bonds holding your flesh and bone together would be overwhelmed by the tidal forces. Your body would be stretched into a long, incredibly thin stream of subatomic particles flowing down into the darkness like a single strand of pasta. But here is a strange, counterintuitive twist of physics. The size of the black hole determines exactly when this violent death happens. If you jump into a small stellar mass black hole, one that is only 10 times the mass of our Sun, the event horizon is very close to the center. Because the radius is so small, the gravity gradient is incredibly steep. The difference in pull over the distance of a human body is enormous. You would be spaghettified and torn apart thousands of miles before you even reach the event horizon. You would die out in visible space. But if you jump into a supermassive black hole, like the monsters at the center of galaxies, which weigh billions of times more than our Sun, the geometry is very different. The event horizon is massive, sometimes wider than our entire solar system. Because the radius is so huge, the gravity gradient at the edge is surprisingly gentle. The difference in pull between your head and your feet is negligible. You could drift across the event horizon of a supermassive black hole completely unharmed. You would not even feel it happen. You would cross the absolute point of no return alive, looking out at the universe behind you, entirely unaware that your fate was mathematically sealed. You would still be spaghettified eventually, but it would only happen deep inside the hole, just moments before you hit the singularity. If you were to watch a friend fall into a black hole, a terrible idea for a weekend trip, you would witness something impossible. You would see them freeze in time. To understand why, we have to look at the second half of Einstein's theory. he realized that space and time are not two separate things. They are woven together into a single fabric, space-time. Because a black hole bends space so violently, it must also bend time. According to general relativity, gravity slows time down. The stronger the gravitational pull, the slower the clock ticks. Even on Earth, this is true. A clock at sea level, closer to the center of the Earth, ticks slightly slower than a clock on top of Mount Everest. The difference is incredibly tiny, mere fractions of a nanosecond, but it is real. The GPS satellites orbiting our planet have to constantly correct their internal clocks to account for this difference. Otherwise, our navigation apps would fail within hours. But near a black hole, this effect goes from microscopic to absolute. Let us say you are watching your friend fall toward the event horizon from a safe distance in your spaceship. As they fall deeper into the gravity well, the time dilation becomes extreme. To your eyes, your friend would appear to move in slow motion. If they tried to wave to you, their hand would take hours, then days, then years to complete a single arc. As they reach the exact edge of the event horizon, their image would stop completely. To your perspective, they never actually cross the line. Time for them, relative to you, has ground to a halt. They would simply hang there on the edge of the abyss, perfectly still. Eventually, they would fade from view. This is because the light bouncing off them is struggling to climb out of the gravity well. As light loses energy fighting gravity, its wavelength stretches out. Visible light stretches into red light, then infrared, then radio waves, until it drops off the detectable spectrum entirely. This is called gravitational redshift. Your friend would turn red, then dim, then vanish entirely, leaving only a ghost image frozen at the edge of reality. But what does your friend experience? This is the mind-bending part of relativity. From your friend's perspective, time is ticking completely normally. Their watch ticks at 1 second per second. Their heart beats at a normal rhythm. They do not feel themselves slowing down at all. They simply fall straight across the event horizon and down into the dark. However, if they were to look back out at the universe as they fell, they would see the opposite of what you see. Because their time is running so slowly compared to the outside world, they would see the rest of the universe running in fast forward. They would watch stars orbit galaxies in seconds. They would watch civilizations rise and fall. In the brief moments before they hit the singularity, they would watch the entire future history of the cosmos play out like a time-lapse movie. At the edge of a black hole, time is no longer a shared experience. It is a private bubble, warped beyond recognition by the ultimate victory of gravity. A black hole is defined by what it traps, but it is made visible by what it has not yet swallowed. If a black hole sits perfectly alone in empty space, it is truly invisible. But most black holes are not alone. They live in the crowded suburbs of galaxies, surrounded by gas clouds and orbiting stars. When a black hole's gravity captures a passing star or a cloud of gas, that material rarely falls straight in. In space, almost everything is moving sideways relative to everything else. As the gas is pulled toward the black hole, this sideways motion is amplified by the conservation of angular momentum, the exact same physics that makes a figure skater spin faster as they pull their arms in. Instead of plunging directly into the event horizon, the material begins to swirl around it. It forms a massive, flattened hurricane of gas and dust. We call this an accretion disk. You can think of it like water circling a drain. But unlike water, The gas in an accretion disk is not moving at a uniform speed. The physics of orbits dictates that material closer to the center must move much faster than material on the outer edges to keep from falling in. This difference in speed creates a violent environment. The inner rings of gas are whipping around the black hole at a significant fraction of the speed of light, while the outer rings lag behind. The gas layers constantly rub and crash against each other. This rubbing creates friction, and on a cosmic scale, friction creates unimaginable heat. As the gas spirals closer to the event horizon, the friction heats it to millions of degrees. At these temperatures, atoms cannot hold themselves together. The electrons are stripped away from the nuclei, turning the gas into a swirling soup of electrically charged particles, a plasma. This superheated plasma glows. It glows so intensely that it produces high-energy radiation, primarily in the form of X-rays. This is the great irony of black holes. The objects that trap all light are actually responsible for the brightest light shows in the universe. When astronomers use space telescopes to search for black holes, they are not looking for dark spots. They are looking for the blinding, blazing X-ray flares of an accretion disk consuming a meal. The disk is the waiting room for oblivion. Matter can orbit in this disk for thousands of years, slowly losing energy to friction and radiating heat away, spiraling closer and closer. But not all of it crosses the point of no return. The accretion disk is such an extreme environment of magnetic and physical forces that it actually powers the most violent ejections of matter in the cosmos. If the accretion disk is a cosmic drain, you might expect everything that gets caught in the swirl to eventually fall into the darkness. But the universe has a violent loophole. Black holes are not just eaters of matter, they are also the most efficient engines of creation in the cosmos. As the superheated plasma, a soup of electrically charged particles, whips around the event horizon, it generates colossal magnetic fields. Because the inner rings of the disk spin much faster than the outer rings, these invisible magnetic field lines are dragged, stretched, and twisted. Imagine winding a rubber band on an airplane propeller. As the propeller spins, the rubber band gets tighter and tighter, coiling in on itself until it is ready to snap. At the very inner edge of the accretion disk, just fractions of an inch from the absolute point of no return, these tightly coiled magnetic fields form a vertical funnel. They grab a portion of the incoming plasma, rip it away from the gravitational death spiral, and accelerate it outward. This material is shot away from the black hole's north and south poles at up to 99% the speed of light. These are called relativistic jets. The black hole acts as a naturally occurring, galaxy-sized particle accelerator. These jets can be so incredibly powerful that they punch through the entire host galaxy and shoot millions of light years out into deep, empty space. When a supermassive black hole at the center of a galaxy is actively feeding and firing these jets, it transforms from a silent, invisible trap into the brightest object in reality. We call this entire glowing system an active galactic nucleus, AGN. If the geometry aligns perfectly, and one of these blinding jets happens to be pointed directly at Earth like a flashlight, we give it a special name, a quasar, short for quasi-stellar radio source. A single quasar can emit thousands of times more energy than our entire Milky Way galaxy. It can easily outshine all of its hundreds of billions of host stars combined. Because quasars are so unimaginably bright, telescopes on Earth can see them from across the entire observable universe. When we look at a quasar that is 10 billion light years away, we are looking 10 billion years back in time. We are seeing the universe in its violent youth, an era when galaxies were colliding constantly, and supermassive black holes had an endless buffet of gas to feed on and ignite. So, the very objects famous for trapping light are, paradoxically, the lighthouses of the cosmos. Up to this point, we have been talking about black holes born from the death of a single star. We call these stellar mass black holes. They are relatively small, usually between 10 and 100 times the mass of our Sun. They are scattered throughout the galaxy like cosmic landmines. But there is another class of black hole. These are not just heavy, they are incomprehensibly massive. We call them supermassive black holes. These monsters weigh anywhere from millions to tens of billions of times the mass of our Sun. And unlike their smaller cousins, they do not wander. They sit in the exact center of almost every large galaxy in the universe. Our own Milky Way is no exception. If you look toward the constellation of Sagittarius, past the dense clouds of gas and dust in the galactic core, you will find a quiet, invisible giant known as Sagittarius A star. It is the gravitational anchor of our galactic home. It contains the mass of 4 million suns, all crushed into an event horizon that would easily fit within the orbit of our solar system's innermost planets. For decades, we only knew it was there by watching the stars around it. Astronomers observed giant, glowing stars whipping around an entirely empty patch of space at millions of miles per hour. The only thing with enough gravity to fling stars around like toys, without giving off any light of its own, is a supermassive black hole. These supermassive objects act as the central hub of a galaxy. Just as the planets orbit the Sun, the billions of stars in a galaxy orbit this central dark mass. They are the seeds around which galaxies cluster and grow. But this raises one of the most glaring mysteries in modern astrophysics. How did they get so incredibly big? A black hole grows by feeding on gas, dust, and passing stars. But there is a strict physical limit on how fast it can eat. We call this the Eddington limit. As gas falls into the accretion disk, it heats up and shines brightly. But light itself exerts a physical pushing force, radiation pressure. If the black hole eats too quickly, the disk becomes so unimaginably hot and bright that the outward pressure of the radiation literally blows the incoming gas away. The black hole chokes on its own meal. Because of this speed limit, it should take many billions of years for a stellar mass black hole to grow into a supermassive one. Yet, when astronomers look at the farthest edges of the observable universe, which means looking back in time to the very dawn of the cosmos, they see quasars, powered by black holes, weighing billions of solar masses. These monsters existed just a few 100 million years after the Big Bang. The math simply does not work. They did not have enough time to grow that large by feeding normally. It is like walking into a hospital nursery and finding a fully grown adult sitting in a crib. How did they get there? Some physicists believe in the direct collapse theory. In the extremely early universe, massive, primordial clouds of pure hydrogen gas might have bypassed the star formation phase entirely. Instead of fragmenting into millions of normal stars, the entire massive cloud might have collapsed under its own immense weight, instantly forming a seed black hole tens of thousands of times heavier than the Sun. This would give the black hole a massive head start. Others believe that early black holes lived in such dense clusters that they constantly collided and merged. By smashing into each other, they could bypass the feeding speed limit and combine their masses in violent gravitational shockwaves. Whatever the answer is, It is clear that supermassive black holes are not just the graves of dead stars. They are a fundamental architectural pillar of the universe itself. A black hole is often described as the ultimate cosmic roach motel. Matter checks in, but it doesn't check out, because nothing can travel faster than light, and the escape velocity exceeds the speed of light. Physicists long believed that black holes were immortal. Once they formed, they would sit in the dark forever. But in 1974, a young physicist named Stephen Hawking realized that if you look closely at the event horizon using the bizarre rules of quantum mechanics, the picture changes completely. Quantum mechanics tells us that empty space is not actually empty. If you zoom in on a perfect vacuum, it is a boiling, chaotic soup of energy. According to the uncertainty principle, pairs of virtual particles, a particle and its exact antiparticle, are constantly popping into existence out of nothing. They appear, instantly collide, and annihilate each other in a fraction of a microsecond. This is happening everywhere in the universe, all the time. But Hawking asked a brilliant question. What happens if a pair of these virtual particles pops into existence right on the razor-thin edge of the event horizon? Imagine this pair appearing exactly on the boundary. Before they have a chance to crash back together and annihilate, the intense gravity of the black hole grabs one of them and pulls it across the point of no return. The other particle, left without its partner, is suddenly free. It escapes into deep space. To an observer looking at the black hole from the outside, it looks exactly like the black hole just emitted a particle. It is glowing. This faint, invisible glow of escaping particles is called Hawking radiation. But there is a catch. One of the most unbreakable laws of physics is the conservation of energy. Energy cannot be created from nothing. Because the escaping particle has positive mass and energy, the particle that fell into the black hole must act as negative energy to balance the cosmic accounting books. When that negative energy falls into the black hole, it subtracts from the total mass of the whole. This leads to a mind-bending conclusion. Black holes are not immortal. They are leaking. They are slowly evaporating into space. For a giant, supermassive black hole, this process is agonizingly slow. It is swallowing background radiation from the universe much faster than it is leaking Hawking radiation. It would take a Google years, a 1 followed by 100 zeros, for a supermassive black hole to evaporate completely. However, as a black hole loses mass and shrinks, the curve of space-time at its horizon gets sharper. This makes the quantum evaporation happen faster. The smaller the black hole gets, the hotter it glows and the faster it leaks. In its final moments, when it has shrunk down to the size of a subatomic particle, it will release all its remaining energy in a single, blinding explosion. Ultimately, given enough trillions of years after all the stars have burned out, even the mightiest supermassive black holes will boil away into nothing but a flash of light, leaving the universe completely dark and empty once again. Hawking's discovery that black holes eventually evaporate and disappear sounds like a tidy end to the story. But in the world of physics, it triggered a crisis. It created a contradiction so severe that it threatens to break our fundamental understanding of reality. It is known as the information paradox. To understand it, we have to talk about how the universe keeps score. In quantum mechanics, there is an ironclad rule. Information can never be destroyed. Imagine you take a hardcover book and throw it into a campfire. To your eyes, the book is gone, turned into ash and smoke. But to the universe, the information of that book, the exact arrangement of its atoms, the specific ink on the pages, is not lost. It is just scrambled. If you had a supercomputer powerful enough to track every single molecule of smoke, every flake of ash, and every photon of heat emitted by the fire, you could theoretically run the laws of physics backward and perfectly reconstruct the book. The universe always remembers. But what happens if you throw that same book into a black hole? According to general relativity, the book crosses the event horizon, gets crushed into the singularity, and adds its mass to the black hole. Then, according to Stephen Hawking, the black hole slowly leaks that mass away as Hawking radiation. Here is the problem. Hawking's calculations showed that this radiation is completely random. It is featureless thermal heat. It contains absolutely no information about what fell into the black hole. When the black hole eventually evaporates into nothingness, the book is gone, and the radiation left behind has no memory of it. The information has been permanently, irrevocably deleted from the universe. Physics is broken. If information can be truly lost, then quantum mechanics, the most successful scientific theory in human history, is fundamentally wrong. But if information is somehow saved, then Einstein's theory of relativity or Hawking's math must be wrong. Physicists have spent decades at war over this. One of the most mind-bending proposed solutions is the holographic principle. Some physicists suggest that when the book crosses the event horizon, its 3D physical form is crushed, but its information is left behind, smeared across the 2D surface of the horizon like a barcode. As the black hole evaporates, the departing Hawking radiation brushes against this barcode, picks up the scrambled information, and carries it back out into the universe. The book is destroyed, but the universe still remembers it. If this is true, it implies something astonishing. A 3D object can have all of its defining information stored on a 2D surface. And if it works for a black hole, some physicists argue it could work for the entire cosmos. It raises the haunting possibility that our three-dimensional universe is actually just a projection, a hologram, generated by information encoded on a distant, two-dimensional boundary. For exactly 103 years, black holes were nothing more than ink on paper. They were mathematical predictions, and later, invisible sources of gravity that we could only detect by watching how they threw other stars around, or by measuring the X-rays of their accretion disks. But no human being had ever actually seen one. How do you take a photograph of an object that traps light? You don't. You take a photograph of its shadow. In 2019, an international team of scientists achieved what was long thought to be impossible. They captured the first direct image of a black hole's event horizon. Specifically, the supermassive monster at the center of the Messier 87M87 galaxy, located 55 million light-years away. To understand how staggering this achievement is, you have to understand the scale. M87 star, the black hole, is massive, about 6.5 billion times the mass of our sun, but it is so far away that taking a picture of it is like standing in New York and trying to photograph a specific dimple on a golf ball sitting in Los Angeles. A telescope's ability to zoom in, its resolution, is directly tied to the size of its dish. To see something that incredibly small in the sky, you would need a telescope the size of the entire Earth. Since we cannot build a satellite dish that large, astronomers used a trick called interferometry. They took 8 existing radio observatories scattered across the globe, from the mountains of Chile to the ice of the South Pole, to the volcanoes of Hawaii, and linked them together. They created a virtual, Earth-sized lens called the Event Horizon Telescope, EHT. To make it work, every telescope had to look at the exact same spot in the sky at the exact same time, synchronized by atomic clocks that lose only 1 second every 100 million years. They collected so much raw data, petabytes of radio waves, that it could not be sent over the internet. The hard drives literally had to be flown on airplanes to supercomputers in Germany and the US to be stitched together. When the supercomputers finally cleared the noise, the image that emerged matched Einstein's century-old equations perfectly. It looked like a blurry, glowing, asymmetrical orange donut. What you are looking at in that famous image is not the black hole itself. The bright orange ring is the superheated plasma of the accretion disk, emitting radio waves as it swirls at near light speed. Notice that one side of the ring is brighter than the other. This is called relativistic beaming. The glowing gas on the bright side is moving toward us so fast that its light is physically bunched up and amplified. The gas on the dim side is moving away from us, so its light is stretched and dimmed. But the most important part of the photograph is the dark circle in the middle. That is the shadow of the event horizon. It is the silhouette of the abyss, silhouetted against the glowing gas behind it. In fact, because the black hole's gravity is so intense, it acts as a gravitational lens, bending the light from the back of the accretion disk over the top and bottom so we can see it. You are simultaneously looking at the front, top, and back of the disk all at once. We finally have our proof. The monsters in the dark are real, and they look exactly like the math said they would. We have followed gravity to its absolute limit. We have watched it crush stars, trap light, shatter time, and erase information. But what happens if we push the math of general relativity even further? What lies on the other side of the singularity? When physicists play with Einstein's equations, they find strange, speculative structures hiding in the numbers. The first is the white hole. If a black hole is a region of space where nothing can escape, the math perfectly allows for the exact opposite, a region of space where nothing can enter. A white hole is a black hole running in reverse. Instead of an event horizon that you can only cross going inward, a white hole has a horizon that you can only cross going outward. It violently ejects matter and light, and absolutely nothing, not even light, can fight its way inside. While the math permits them, physicists do not believe white holes actually exist. The laws of thermodynamics, specifically entropy, which says the universe must move from order to chaos, strongly forbid a star from suddenly uncollapsing itself out of nothing. But what if a black hole and a white hole are connected? In 1935, Albert Einstein and Nathan Rosen discovered that the sinkhole of a black hole could technically be extended. Instead of ending in a singularity, the funnel of infinite curvature could punch all the way through the fabric of space-time and connect to a white hole in another part of the universe, or even another universe entirely. This is an Einstein-Rosen bridge, more commonly known as a wormhole. In theory, a wormhole is a cosmic shortcut. You could fall into a black hole in the Milky Way and instantly be spat out of a white hole in the Andromeda Galaxy, millions of light years away, bypassing the speed of light entirely. However, there is a catch. The math shows that the throat of this wormhole is incredibly unstable. The moment a single photon of light or a spaceship enters the black hole, The gravity of that object causes the throat to collapse and pinch off instantly. To keep a wormhole open, you would need to prop it up with exotic matter, a theoretical substance with negative mass that pushes space-time outward instead of pulling it inward. As far as we know, exotic matter does not exist. For now, wormholes and white holes remain ghosts in the machine of physics. But what we do know is the ultimate fate of the black holes that actually exist. They are the final act of the cosmic play. Trillions of years from now, long after the last star in the universe has exhausted its fuel and faded to a cold, dead cinder, the universe will enter the black hole era. The night sky will be completely pitch black. The only dominant structures left in reality will be supermassive black holes, quietly ruling over graveyards of dead galaxies in a freezing, expanding void. But as we learned from Stephen Hawking, even they are not eternal. Over unthinkably vast stretches of time, they will slowly leak their mass away through Hawking radiation. They will shrink, glow hotter, and finally detonate in a flash of gamma rays. When the final supermassive black hole evaporates, the universe will be left completely empty. No stars, no planets, no atoms, no light, just a cold, thin soup of scattered photons cooling toward absolute zero. Gravity will have finally won, and in its victory, it will erase itself.